Hello, my dear students. Good morning, all of you. Today we are going to start exercise of chapter 9, and today we will start from exercise 9.1. A steel wire of length 4.7 meter and cross sectional area 3.0 into 10 raised to minus 5 meter square stretches by the same amount as a copper wire of length 3.5 meter and cross sectional area of 4.0 into 10 raised to minus 5 meter square under a given load. What we need to calculate? What is the ratio of the Young's modulus of steel to that of copper? Right. So here we have given two different wires, steel wire as well as copper wire. Right. So first of all, we have given steel wire, and for that we have given the length of steel wire, which is considered as LS, and which is equal to 4.7 meter, and cross sectional area of steel wire is also given, right? So AS equal to 3.0 into 10 raised to minus 5 meter square, and we have another wire, copper wire, having a length, copper wire having a length CU, which is equal to 3.5 meter, length of copper wire, which is denoted as LCU. And similarly, area of copper wire, which is ACU, is also given 4 into 10 raised to minus 5 meter square, right? And what is the ratio of Young's modulus of steel? So here we need to calculate Ys divided by Ycu, Young modulus of steel to that of copper, ratio of Ys to Ycu, that we need to calculate, right? Now one more thing, here it is given this both the wire stretches by the same amount. This both the wire, copper wire as well as steel wire, stretches by the same amount. It means the force of copper wire, which is equal to force of steel wire, equal to F, right? Because the it is stretches by the same amount, it means the forces, or you can say load, on both the wires are same, and that's why we can consider FCU equal to Fs equal to F, right? Force on copper wire equal to force on steel wire equal to F, right? And if we have given the same force, if we have given the same force to both the wires, elongation, elongation means change in length, is also same. Change in length for both the wire also same, right? So here delta LCU equal to delta LS means change in length in copper wire equal to change in length in steel wire equal to delta L, right? Here we have applied the force, applied the load on the both the wire are same. That's why the change in length is also same for both the wires, right? So here we have two equations for solving this example. Now we know Young modulus Y, which is given by ratio of stress to strain, right? Ratio of stress to strain is known as Young's modulus. stress which is also defined as force per unit area, and strain which is change in length to original length, right? Strain is given as delta L by L. So here we have this equation for Young's modulus, right? Now let's simplify this equation. F by A into L by delta L. So this is the general equation for Young's modulus. Now let's write this equation for copper wire as well as steel wire. So first of all, for steel wire, Ys equal to force on steel wire divided by area of steel wire into length of steel wire and elongation change in length of steel wire. And similarly, Y copper equal to FCU divided by ACU into LCU divided by delta LCU, right? So let's divide it because we want here Ys by YCU. So Ys by YCU equal to, so we have equation for Ys, Fs into Ls divided by As into delta Ls into YCU, which is in denominator, right? So it becomes like ACU into delta LCU, ACU into delta LCU divided by FCU into LCU, right? But we know FCU equal to Fs equal to F and delta LCU equal to delta Ls equal to delta L. So the term Fs and FCU will be cancelled out because we can place FCU equal to Fs equal to F in place of Fs and FCU. So Fs and FCU is cancelled out, and similarly delta Ls and delta LCU is cancelled out. So we have finally we have Ls into ACU divided by Ls into ACU divided by As into LCU, right? LCU. And we have all these parameter: length of steel wire, area of steel wire, length of copper wire, and area of copper wire, right? Just put the values in this equation. We will get the ratio of Ys and YCU that we required, right? So here Ls, length of steel wire, which is 4.7 meter, into area of copper wire is 4 into 10 raised to minus 5 divided by As, area of steel wire, 3 into 10 raised to minus 5 into length of copper wire, which is given 3.5 meter. After solving this, we will get the ratio of Ys by YCU is 1.79, which is approximately equal to 1.8, right? So here we have calculated the ratio of Ys by YCU is 1.8, right? So here the answer for Ys by YCU is 1.8, right? So this will be the answer. So the next exercise is exercise 9.5. We have given two wires of diameter 0.25 centimeter, one made of steel and other made of brass, are loaded as shown in figure. So this figure for exercise 9.5. And what we have? We have two wires, one of made of steel and other made of brass, and both having the same diameter, means diameter of steel wire as well as diameter of brass wire, and it is given 0.25 centimeter, right? And the unloaded length of steel wire is 1.5 meter. Unloaded length of steel wire which is given for steel wire, this length is 1.5 meter, and for brass wire it is 1 meter, and for brass wire this length is given 1 meter. And what we need to calculate? Compute the elongation of steel and brass wire. So here we need to calculate elongation. So elongation, which is nothing but it is delta L, change in length. And here we need to calculate elongation for steel as well as brass wire. Delta LS, change in length, or you can say elongation in steel wire, and change in length, elongation for brass wire, that we need to calculate over here, right? So how can we calculate elongation? One more thing, we have given the Young's modulus. Young's modulus for steel, which is 2 into 10 raised to minus 2 into 10 raised to 11 Newton per meter square, and Young's modulus for brass 0.91 into 10 raised to 11 Newton per meter square. It is given, right? Here the length of steel wire as well as length of brass wire is given in meter, that we can see, and here the diameter for steel as well as brass, which is equal and is given in centimeter. So here we need to convert the centimeter into meter for calculation of this example. So for converting this centimeter into meter, 0.25 into 10 raised to minus 2 meter, or you can directly divide by 100, right? So diameter for steel as well as brass equal to 0.25 into 10 raised to minus 2 meter, and for radius RS and equal to RB, which is 0.25 into 10 raised to minus 2 divided by 2, which becomes 0.125 into 10 raised to minus 2 meter. So radius for steel as well as brass is 0.125 into 10 raised to minus 2 meter. Right. Now let's calculate the elongation for particularly steel wire. So first is for steel wire. First we will calculate the elongation for steel wire, and here we have given the Young's modulus for steel wire. So directly write the equation for Young's modulus, which is stress divided by strain, right? Stress is given by force by unit area, and strain is delta L by L. Here we need to calculate for steel wire. So Fs, force on steel wire, As, area for steel wire, delta Ls, elongation in steel wire, and Ls, length of steel wire. So this is the equation for Ys. Now let's simplifying this equation. So Fs by As into this Ls by delta Ls. So I have simplified this equation. Now here we want delta Ls. So write this equation in terms of delta Ls. So delta Ls equal to here Ys, and this is delta Ls. Interchange their position, and equation becomes delta Ls equal to Fs by As into Ls by Ys, right? Now As, area for steel wire, and this is Fs. Now how can we calculate this Fs and As? So here for calculating Fs and As, first we will calculate Fs. Here we have the steel wire, right? And steel wire having the mass of 4 kg. Here the mass is given, and from mass we can easily calculate force. So Fs, force F into mg, right? But here this steel wire having steel wire having only 4 kg mass, but it affects on 4 kg mass as well as for 6 kg mass. So particularly for steel wire, for calculating the force on steel wire, we have to consider the mass of 4 kg as well as the mass of 6 kg. So here Fs equal to mass 6 plus 4 into G, which is 9.8, and 6 plus 4, which is 10 into 9.8, which becomes 98 Newton. So here Fs is 98 Newton that we have calculated. So delta Ls, Fs, which is 98 Newton, divided by area of steel wire. Area is given as pi r square. Pi into r square, and value of r that we have calculated 0.125 into 10 raised to minus 2 and square, because r square is there, right, into length of steel wire. The length of steel wire, which is given as 1.5 meter, so 1.5 divided by ys, Young's modulus, which is given 2 into 10 raised to 11, right. So after simplifying, we will get the value of delta ls is 1.5 into 10 raised to minus 4 meter. So elongation in steel wire, or you can say change in the length of steel wire, which is equal to 1.5 into 10 raised to minus 4 meter. So here we have calculated delta ls. Now in similar way we can also calculate delta lb. So let's calculate delta lb. So delta lb equal to, same equation we can use, right. So delta lb, which is fb, the same equation we can use, fb by ab into lb by yb, right. Now force on brass wire. So for calculating force on brass wire, we will consider only the 6 kg mass, and we know f equal to fb, which is equal to m into g, and mass is here is only 6 kg. So 6 into 9.8 Newton. 6 into 9.8 Newton, the value of FB. So FB is 6 into 9.8 divided by area of brass wire, which is the same as the steel wire. So pi into r square, 0.125 into 10 raised to minus 2 whole square, right, into lb, length of brass wire, which is given 1, so 1 divided by Young's modulus of brass wire, which is 0.91 into 10 raised to 11, right. After calculating, we will get the value of delta lb, which is 1.3 into 10 raised to minus 4 meter. So here we have calculated delta ls and delta lb, elongation in steel wire and elongation in brass wire. So by using the concept of Young's modulus, you can easily calculate the delta ls and delta lb for this exercise, right.